I'm Shane Snyder. I'm going to talk to you guys a little bit about I/O and data management and file systems topics that are of interest for ALCF. So just to kind of set the stage, managing scientific data is an extremely important problem. So on the application end, we have tons of different HPC applications that have like a lot of different diverse access patterns. And there's, what we've observed is there's kind of an explosion of scientific data, not only in terms of volume that these applications are generating, but also kind of in terms of diversity of access. And there's been this longstanding problem in HPC of I/O being kind of a bottleneck. Storage is notoriously slow. And kind of this increasing diversity and data volume on the application side just kind of compounds that problem. So it's an ongoing problem that's probably increasing in intensity basically. And meanwhile, we've seen lots of different hardware storage trends that have enabled design of really kind of high performance storage systems for HPC. And so these are kind of meant to increase productivity of applications by giving them massive amounts of storage resources to absorb what applications are doing, data intensive applications in particular. So ALCF and other HPC facilities, basically they're deploying really vast amounts of storage resources to kind of meet the demands of these applications. And so today we'll talk a little bit about ALCF and the typical HPC data management stack, and in particular how it relates to what ALCF has deployed for users, and so how you can be better aware of what's available and how you can use it effectively. Basically, are kind of the high-level goals for the presentation. So just for a little bit of background, we'll start with parallel file systems. So we'll kind of start towards the lower end of the HPC stack and kind of work up from there to where the applications are, and hopefully that resonates. But we'll start kind of towards the bottom and talk about parallel file systems. So parallel file systems have been really the traditional way of managing user data HPC facilities for decades now, and it's still a big part of the HPC data management stack even today, though it is changing a bit. So parallel file systems are really similar to local file systems that you have on your laptop or on your workstations in some senses, but obviously a lot different in other senses. So as far as similarities go, you're going to interact with them in the same way in terms of how you manage and store your data. So things are going to be organized in your typical file directory hierarchy that we're all very familiar with on our workstations. But the key difference is that they give you a lot more aggregate capacity and performance. And this figure over to the right kind of is meant to demonstrate this. You might have a scientific application with tons of different processes, and you'll use your traditional open, read, write, close calls that we're all familiar with from programming experience to access various data sets that are stored in this hierarchy on the file system. And you can see how different files maybe are backed by different amounts of storage resources and things like that. But the key idea is that there's lots of storage devices under the covers of these file systems that can give you a lot of increased performance compared to just one or two devices you might have on a workstation or a laptop or something like that. So the characteristics, just to kind of be more explicit, that kind of make parallel file systems so important and useful in HPC is that they're high performance. So there's lots of parallel I/O paths that you can take to the data to get better aggregate performance. So you're kind of harnessing the power of numerous devices and getting good performance that way. They're generally scalable, so storage resources you can scale out to meet demands of current and future applications. So it's generally pretty easy to add new resources and get increased performance that way. And they generally have reliability mechanisms, so some ability to fail over upon faults in terms of storage servers or individual storage devices. Generally, parallel file systems have graceful ways of failing over and recovering in those situations. And some examples of popular parallel file systems in HPC include Lustre, GPFS, which was eventually, I think, rebranded as Spectrum Scale and perhaps maybe even rebranded again. I can't keep track. And also BGFS is deployed at some other facilities. So we'll talk a lot about Lustre today because it's the kind of the preferred production file system, parallel file system here at the ALCF, as well as a lot of different other HPC facilities, including the big DOE labs. So Lustre's design is centered around the idea of an object storage service and a metadata storage service. So there's basically these metadata servers that manage different storage devices that manage metadata information. They're called metadata targets. But basically their role is to maintain this coherent file system namespace. So as you kind of create new files or directories and delete things, the metadata servers are tasked with keeping a coherent view of that and maintaining this hierarchy. And they also just kind of keep general information about the data, the files that are being stored. So like which storage servers they're located on and things like that. So metadata servers kind of maintain that consistent view and the detailed information about the file system. And the object storage servers, or OSSs, have their own devices called OSTs that are used to store the actual underlying file data. So there's this kind of decoupling between metadata and data that gives you kind of attractive performance characteristics. You can kind of add more and more object storage targets to get better performance, basically. So the Lustre clients themselves, generally what happens is they'll coordinate with like you'll open a file and there's some coordination between the Lustre client and the metadata server to get a view of the layout of the file. The layout of the file, like which storage servers it's distributed over. And then from that point on, for reading and writing data, the clients talk directly with the object storage servers, so there's no more kind of need to interact with the metadata server. So it kind of creates a separation that is really useful for getting high performance for your bulk data. Another really big key for Lustre files is that they're broken into stripes. And these stripes are round robin distributed over storage servers. And this figure over here on the right's trying to depict this. So basically you have two object storage servers, and each of them is managing two object storage targets, OSTs. And there's an example file at the bottom with 9 stripes, and you can see how they're distributed over the various storage targets. And it should give you a visual, indication of how you're able to get better performance in terms of those 4 different, network paths to each of the storage targets that applications can then take advantage of. So we'll talk a little bit about what your storage options are just generally on Polaris, and then we'll talk a little bit more about how to best practices for how to use them and get good performance. First is Eagle and Grand file systems on Polaris, and these are Lustre, scratch file systems. Basically, they're meant for temporary storage of applications IO-intensive data. So if you're running a big application, generally what happens is you're outputting or reading or writing to or from these specific file systems. They're mounted at Eagle and Grand on Polaris, and there's subdirectories for each project. So I think you guys have maybe already played around with this a bit, but you should see, for instance, under, I believe, Grand, there's a project directory, ALCF training that we're using for this particular workshop. They do have an ability for community sharing of data with Globus. We'll talk more about that in a little bit. They have 100 petabyte aggregate capacity, so they can store a ton of data, 656 gigabytes a second transfer rate. And to give more details on the Lustre configuration, there's 160 different storage targets and 40 different metadata targets. So basically 160 different devices that you can stripe your data across. There's also the home file system, which is again Lustre, but it's kind of got a different purpose, as you might imagine. So it's meant for just general storage of data that's not IO intensive. so binaries and source code and things like that. This is definitely not where you would want to, output or read from your large scale, jobs that are running on the compute nodes. Your performance is not going to be nearly as good, and I'm sure the ALCF operations people would appreciate if keep your IO intensive stuff on the scratch file systems. Again, home file systems mounted at home. There's subdirectories for each user. I'm sure if you used shared workstations or systems in the past, you're familiar with that kind of setup. There are regular backups to tape, which is helpful. It's not something you get on the scratch file systems, but it does give you some, ability to fall back if you have some issues with data in your home directory. And there's a default quota of 50 gigabytes for each user there. Lastly, there's node local storage. So basically SSDs with the XFS file system. And these are meant for temporary compute node local storage for your jobs. And these are mounted at local scratch on each compute node. And again, it's 2 SSDs with about 3 terabytes of capacity. One thing and we'll talk about this in a bit, but one important thing is that users must copy this data somewhere else persistent at job end. There's no sort of management of the data that's stored there. That's up to the user explicitly. So yeah, the key thing here is there's different options, but you should always be mindful about what's available for you and what the intended use of the storage resources are. So this can not only increase the performance of your applications, but it can just lead to general more efficiency on the system, and it can also not give you any surprises whenever it comes to data integrity. So that's important. So we'll spend a little bit of time talking about Lustre file systems and how to get the best performance from those at ALCF. So the key here tends to be file striping settings that we kind of talked about briefly. So one of the important things is that this may be a surprise to ALCF users is that the default Lustre stripe settings is just across a single OST. So there's just a single stripe whenever you create a file on Lustre at ALCF. So this is really helpful for maybe smaller files or not IO intensive files, but if you've got like a really large shared file that your application is accessing, then this is really not optimal in terms of storage performance because you're constraining yourself to being stored on a single device. So all that to say basically that you really need to think carefully about striping settings for IO intensive files to get the best performance. And so there's a tool that's available that you can use to modify stripe settings. So this LFS set stripe tool you can run yourself, and you can give it a file or a directory name, and you can change the default behavior from a single stripe to multiple stripes, and you can also increase the size of the stripes too. Just a quick demonstration of how this works. So whenever you first create a file or a directory on these file systems, again, the default stripe setting is just going to be 1. So we make a directory and run LFS get stripe on it. The stripe 4 directory, you see it's got a default stripe count of 1. And one thing to keep in mind is for directories, all files that are created within that directory will inherit the same stripe setting. So any file that you create in this directory will just get the same stripe configuration, basically. If you instead do LFS set stripe -C4 to give it a stripe count of 4, then you can see that the LFS is reporting a stripe count of 4 in this case, in which case, again, the data will be distributed across 4 servers and give you, ideally, better performance. There is, I think, merged into the hands-on GitHub repository, there's an example that demonstrates how to set this file striping and also runs a benchmark before and after setting some striping settings that gives you some performance discrepancies so you can run to really kind of hammer this home. So there's this Lustre striping example. It's basically a job script that you can run and get some benchmark output that you can inspect closer. So if you're interested in kind of tinkering around with this a little bit more, have a look at that and see if you can run it and examine the output to see if it makes sense. As far as recommendations in terms of striping, because we've just kind of, basically to this point, it's been just, a nebulous, more stripes is better for performance. But that's not necessarily always the case. Again, so it's important to think about this, thoughtfully, basically. So there are ALCF suggestions for Lustre stripe settings that you certainly can't go wrong in kind of following this sort of advice. So one thing to notice is that for file per process, so each application process is maybe creating or accessing their own file, and also small file workloads. So regardless of whether they're file per process or shared, the general strategy is the same, and it's convenient that it's basically just use the default stripe settings. So use a default stripe count of 1, and use a default stripe size of 1 megabytes in both of those cases. And again, in file per process and small file, it really kind of is helpful to restrict the I/O to a single storage server, as opposed to trying to stripe across more. So that's an example of where striping more isn't necessarily always the most efficient or performant strategy. On the other hand, for shared files, and particularly larger shared files, you're going to benefit a lot more from more storage resources. ALCF recommends, 48 OSTs per file for large files, so for files greater than 1 gigabyte. And you can also experiment with larger stripe sizes between 8 and 32 megabytes. So there are probably sweet spots for different workloads in there, but you certainly can't go wrong with just this general rule of thumb for shared file and for file per process. And this LFS set stripe command is an example of how you would maybe configure, for a larger file, a stripe count of 48 and a stripe size of 16 megabytes. Just a concrete example showing some performance for a benchmark using different striping settings. So this was a 128 node run of the IOR benchmark on Polaris. So this is definitely a larger scale job. I think this is maybe roughly a quarter of the machine. And you can see how varying the stripe count for this workload varies the performance that you can attain. Maybe most noticeably is that there is a point, you're getting increased performance as you add more and more stripes, which makes sense. But maybe as you get to the larger end of stripe counts, you start to see what looks like more variability and also kind of like a tailing off of the performance. So this is probably part of the reason why using 48 servers or less than the total number of 160 might be beneficial. And the reason for this, I think, is that if you stripe across all servers, that kind of gets you more susceptible to straggler OSTs. So maybe one or a handful of these OSTs is a little bit slower, but now you've got to wait on all of them. Whereas maybe if you did like a quarter of the available OSTs, it can give you the ones that are maybe not as heavily loaded and things like that, and it can just generally give you a little bit more tighter variability on your performance, basically. So I would say that striping across all of the servers doesn't appear to be a net win. So keep that in mind. One thing I'll mention quickly, though, even though it's not necessarily the default behavior on ALCF file systems right now, is that there's this new Lustre feature called progressive file layouts that enables a more flexible file striping strategy. And the idea is that you basically set different regions in a particular file that have different striping configurations. So you can see on this one, there's a few different components. So 0 to 2 megabytes, 2 megabytes to 256 megabytes, and then 256 megabytes to the end of the file. And each of those has different configurations in terms of number of stripes and stripe size. And so basically what this allows you to do is it allows you to have dynamic striping, basically. So smaller files that are less than 2 megabytes will always just be on a single storage server. But as you start accessing further and further into the file, it starts to be striped a little bit differently. So it's kind of just like a really convenient way of maybe setting striping settings that are more generally performant for a variety of different workloads. So it could be something that's of interest of interest to you. If maybe you want to find an optimal, default setting for your application or your workflow or whatever. And also just something to generally keep in mind if this, becomes the strategy at ALCF employs it at some point. So again, yeah, not enabled by default on ALCF systems, just something to keep in mind. And ultimately, you're always going to get best performance by manually setting striping yourself and being kind of explicit. So, for larger shared files, using the recommended settings, and for smaller files. But PFL, progressive file layouts, is just like a configuration that's going to be hard to get terrible performance out of. So it still has its usage. One other thing we'll briefly mention about Lustre file systems is that they do have quotas that you need to be aware of. There's this My Quota tool that you can run from a login node to get an idea of where you stand on your usage of different directories. You can see here it shows you both your home directory, which is on a per user basis, as we mentioned earlier, what your capacity is at, as well as for your various project directories, what your used capacity is at and what your quota is. And again, the project directories are shared across all users in that project. It's not like a user-specific thing. I want to talk briefly about the node local SSDs. So for some workloads, it may be beneficial to try and use the node local devices as like a sort of a cache, basically, between you and the parallel file system. So it's going to give you a much lower latency relative to Lustre, which makes sense since it's on the node itself, as opposed to across multiple network hops and storage networks and stuff like that. And it's also not shared with many users. So a Lustre file system is going to be shared with everyone on the system, whereas the node local is just your application, basically. Two really important things to keep in mind, though, if you do use them, is that, again, the data is only visible to processes running on the same node. So if you have an MPI job that spans many nodes, then the data that's stored on the node local devices isn't going to be easily visible to all processes. So just something to keep in mind in terms of data visibility. The other really important thing is that data staging is something that you have to do manually as a user. So in your job script, for instance. So as an example, staging and data, or staging and read data for a job to the node local devices, you might have a initial step where one process on each node copies an input file from the Lustre file system to the local scratch mount point that's for the SSDs, and then you would run your application using that local input file, and that can give you, again, really low latency access to the file compared to Lustre. Similarly, for SSD stage out for job write data, you would first run your application, maybe that's generating a file per process in this local scratch space, and then maybe at the end of the job script, you could have one process on each node copy the contents of that local scratch back out to the Eagle file system to be persisted longer term. So again, the key point here is that it can be a really useful caching layer between you and the file system, but you've got to explicitly move the data to there before you access it and back out to the scratch file system at job end, or else you'll lose it forever. And there's another demo in the hands-on repository that demonstrates how to do the stage in and the stage out and their performance implications. And if one of the interesting performance things that you'll notice if you do run that example is that the write performance is actually really comparable when staging or whenever writing to local scratch versus Lustre, which is kind of at odds with what I just said. The reason for that, I think, is that there's some caching effects for writing to Lustre, and that all of the writes to Lustre are probably going to complete locally and then be flushed out in the background. So you don't really see you see low latency with the Lustre writing too, just like you would with the local SSDs. But caches, you can overrun those quickly. Depending on what your access pattern is, the caching effects may go away. So it's still definitely useful to use for staging and doing node local access there, but something to keep in mind. You should be able to see with the read performance in particular, where you're not able to get that caching effect. The performance to the local SSDs for that example workload was, I think, 10x faster. So definitely something to keep in mind as an option for improving performance. I want to talk a little bit about the different I/O libraries that you have for interacting with file systems. So we've talked, a little bit about the storage system itself, but how do you interact with that from your application or from your library or whatever it is that you work on? So the lowest level of that is what we call POSIX, this portable operating system interface. And basically all file systems expose a POSIX-like interface. So it should be something that's very familiar to everyone with some programming experience. So again, it's basically these standard interfaces for interacting with file systems. So the open, read, seek, and close calls, those are all like POSIX operations that every file system will have some sort of baseline support for. In addition to the interfaces, POSIX is known for its semantics, so that that it's guaranteed by each operation. And in particular, one that's really problematic in HPC is this semantic that successful writes to a file must be immediately visible to subsequent reads. So basically, anyone who writes to a file, anyone that reads from it at a later point in time should immediately get that data. As you can imagine, this is really tricky to enforce on parallel file systems. So there's lots of different devices that are kind of combined into this really big coherent system. So having this coherence between all the different servers and devices is really tricky and has its own kind of performance implications for trying to do that properly. So really the upshot here is that POSIX was never really designed or necessarily intended for parallel or large-scale parallel file access. So these inflexible consistency semantics often just result in parallel file systems using kind of like elaborate locking protocols, which will impact your performance, or they just entirely avoid these strong consistency guarantees, in which case it's kind of up to the application to make sure not to, access same regions of the file at the same time and get kind of different results. So so like I said, just basically the best practice now in HPC is to avoid doing concurrent access to the same regions of the file, to avoid, getting inconsistent data, or to avoid using these elaborate locking protocols, which are can hamper performance. The MPIO interface was designed to help kind of address these parallel I/O needs of HPC applications. So basically the idea is to allow MPI programs to read and write using parallel I/O strategies. So things like to a single shared file, things that are not natively supported by POSIX and that are difficult to code yourself. So MPI is a great environment for doing this, unsurprisingly. So it has this notion of collective operations that can be run across all processes that are contributing to some task, whether it be reading or writing data. And it also has MPI data types, which are really helpful for describing the layout of your data, both in memory and in the file. So there's a few different I/O capabilities that allow you to do different flexible I/O strategies that can give you good performance. With MPI, you can still do the traditional independent I/O that you would perhaps be accustomed to with POSIX. So every process is basically issuing independent operations to different storage devices. That works fine enough in a lot of different workloads. There's also collective operations where processes are kind of working together to limit their access to different storage devices. So this figure, basically there's basically some cooperation between the different processes in terms of who's accessing which storage device, which is obviously going to give you a little bit more performance efficiency compared to this, basically all-to-all access for independent operations. There's also non-blocking operations that you can issue, which can be useful in a lot of circumstances where maybe you want to overlap I/O with other activities. And there's just general and system-specific optimizations that MPIO will implement for you that maybe you're not aware of that can give you really good performance under the covers. And as an example, there's this kind of two-phase collective I/O algorithm that's used traditionally whenever you use MPI collective routines. And basically what it does is it takes, what is a, an all-to-all collective read or write of data, and it reorganizes the different phases of I/O so that it kind of restricts to specific aggregator processes. It basically makes those the parties that are responsible for interacting with the file system. So it reduces the number of people that are trying to access the file system, and it allows you to basically shuffle around data in a smart way that gives you better performance. And Rob Latham, a coworker of mine, is going to be talking about MPIO tomorrow in one of the parallel sessions. So if you're interested in learning a little bit more about MPIO in general and things like this collective I/O optimization, then I'm sure that that session will be really useful for that. So MPIO is definitely a good step in the right direction. For HPC applications, it solves the kind of parallel I/O access and getting good performance with that sort of strategy. But it's still not quite there in terms of what most applications prefer. With MPIO, you're basically still looking at files, as like your data is stored at specific offsets and things like that, and kind of maintaining lots of different scientific variables and stuff like that in a file where you're trying to keep track of which variable is stored at which offset and things like that is not necessarily fun or enjoyable, or it doesn't always work out well either. So things like HDF5 are really popular with HPC applications for this reason. So they take MPIO and go a step further basically and kind of give you this really nice data abstraction for scientific data. So for storing, multi-dimensional arrays and things like that, you can basically think about a file containing lots of different data sets that you can access independently and not have to know about like exactly where they're stored and things like that. So it's really kind of convenient for application scientists and things like that who don't want to write their basically own file formats and whatnot. They can use HDF5 to manage this for them. So yeah, basically a HDF file is a lot like a container rather than just like a file. And again, there's really nice interfaces for letting you access entire data sets or subarrays or individual elements in data sets. There's lots of different ways for slicing things up and things like that. It has support for collective I/O using MPIO or just independent I/O with POSIX, so you can take advantage of, again, the parallel I/O support that MPIO has. And it also has a vol layer, which is basically a virtual object layer that allows you to write your own abstract implementation of storage devices. All that basically means just that, as new storage systems that are maybe not parallel file systems are available, then HDF5 has an ability to kind of map the data abstraction onto different types of storage devices. So it really lets it be more applicable in more situations. And again, Rob Latham is also going to have a second talk tomorrow on HDF5. So if you'd like to learn more about HDF5, then for sure check that out. Okay, so that's kind of our journey up the stack. So we'll just kind of highlight the key takeaways here. So above the I/O hardware, there's parallel file systems, things like Lustre, which maintain your logical file model and provide like a POSIX-like interface that you can use for accessing individual files and directories. There's this transformations layer that's above the parallel file systems, kind of like I/O middleware like MPIO that's responsible for reorganizing parallel accesses and optimizing them so they can get the best performance out of the parallel file system. They tend to know lots of secret optimizations for file systems like Lustre. So there's really a lot of performance gains to be had by using this sort of middleware layer to reorganize things in an optimal way. And then at the top layer, there's your data model. So this is something that the application interacts with directly and has better support for scientific data and portable file formats and stuff like that. So that would be like HDF5 and ParallelNet CDF and Audios, if you're familiar with those. I want to briefly mention the ALCF Community Data Co-op, ACDC. It's not something that I've used myself, so I had to educate myself a little bit before the call, or before the talk. Nothing super detailed here, but just for some background, it's a service ALCF is offering to give you a platform that enables sharing of data with external collaborators and also services for data discovery and analysis. So basically solving a long problem with how do you share data with collaborators without requiring them to get ALCF accounts or without copying things to Box and sharing links and stuff like that. So it's something that's very useful, and I think there's a lot of different projects that are already using this and have nice little interfaces for searching and discovering data as it's generated on these systems. And all this is based on Globus, which Greg is going to talk to us about here in a little bit. But if you're interested and think it could be relevant for your project, then I have the link here where you can go learn more. But again, if you have a data management problem for external collaborators, this could very much be something that could be of use for you. The last thing I'll talk about is kind of a complementary thing. So how do you analyze application IO behavior? So tools for doing that. It's pretty complicated. There's like lots of different layers and lots of different interfaces or storage systems that could be used under the covers. So it can be a lot to kind of grapple with as a user, but tools like Darshan, which I work on, are meant to kind of help with this complexity. So Darshan is basically a lightweight tool that integrates directly into your applications that run at ALCF. It'll capture a lot of detail, so it will intercept all of the IO calls your application makes, grab some statistics, store all that information in a log file, and then you can analyze that log file after the job is finished. And so we have these kind of summary reports like I have over here on the right side, just as an example, that give you, a lot of kind of information about the IO behavior of your job. And this can be really useful for understanding, what exactly it is your job's doing from an IO perspective, what performance you're getting, how much data you're reading and writing, how many files you're accessing, things like that. And if you want to learn more, I have the Darshan project website here at MCS. We'll give you information on how to build certainly the analysis tool or the log file analysis tools are things that you'll probably have to build manually to generate reports like this, but Darshan data should be gathered automatically for jobs that are running on Polaris. So at least that part should be taken care of. And just as again, so this is the Darshan job summary report, which is generally our starting point for looking at Darshan data. So it basically just takes a log file as input and generates an HTML file that you can view in your browser to view all these kind of key IO performance characteristics. So it's just some quick examples. It gives you detailed job metadata. So, your job ID, the number of processes you used, how long it took your application to run, the exact command line that you used. It gives you heat maps of IO activity. So across a number of different interfaces, it can tell you like which processes are doing IO at certain times and things like that, which can be really helpful for visualizing bottlenecks and hotspots and things like that could be degrading your IO performance. And again, there's also kind of IO statistics for different layers of the stack. So you can see your general read and write bandwidths at the MPIO or POSIX layers and stuff like that. So it's really kind of a helpful way for just getting a high level understanding of your IO performance, which you could maybe use to sanity check different configurations or things like that for your application to see if you're getting good IO performance. Okay, so just a quick recap. So we've talked about a lot of the various software technologies that make up the traditional HPC IO stack, which we use to manage user data sets at ALCF. So parallel file systems at the very bottom offer you really high performance scalable storage. IO libraries are what your applications will use directly to interact with the file systems, with POSIX being this lowest level that interacts directly with the file system, with MPIO on top of that, providing you parallel access capabilities and things like HDF5 above that, kind of bridging the gap between application science things and storage abstractions. And then you have, again, tools like Darshan that can help with better understanding and ideally tuning with what's going on. So maybe the key takeaway here is to always look at facility documentation and other resources. A lot of the information I've shared with you, I've scraped from various ALCF documents and websites and presentations and things like that. So there's a lot of resources out there for you if you look in the right spots. So always look for just suggested best practices from facilities and stuff like that, and reach out for help if you need any. And I'm sure folks will be happy to help you figure out your IO performance needs. I think with that, we're right on time. So I go ahead and wrap up.